So,
Okay.
welcome back. We are talking about QGraphics View. Can you even see ourselves? See the slides? Everything's fine?
Perfect.
We have seen the basics of QGraphics View. We've seen the coordinate system stuff, which is definitely going to be a key part when you start working with QGraphics View. The final thing we'll talk about now for the next 15 minutes or 20 minutes or so are custom items in QGraphics View. So you are implementing a 2D version of Wolfenstein. It feels like 3D, but that's because that you're cheating with the kind of wrapping around kind of cheating I did with the house. And now you want to implement your own monsters. And they don't really work out that well with rectangles and individual lines and so on. So you want to paint it yourself. And that's what we're going to talk about now.
Right. We are looking at, well, we will be looking at three main areas in this part. The actual visual representation, so how do you paint your own item on the screen, right? That's obviously the first thing that comes to mind. And then we will look at event handling, so how can I interact with my own item. So if I click on my monster on a specific area, it might trigger some action. And finally, we'll look a bit at collision detection. The API for that is all in QGraphics item. That's an abstract class. So if you want to have your custom item, you have to inherit from that. And at least implement paint, which unsurprisingly will be the method that actually paints the item onto the screen, and bounding rect, which specifies the area in which your item will be shown and how large it is. And usually, unless you have something that's actually shaped like a rectangle, which is probably not the case because that's exactly what we try to avoid here. There's also shape, which will specify the exact shape of your item. And that can be basically anything. Like Jesper's nice rail over there. So you return the entire shape of that thing. And it doesn't even need to be continuous, so it could have holes in it. So any shape you can think of, you can use there. Okay?
Yep. Let's just for a second here. This example here is just, again, to highlight the difference between the bounding rect method, which is just a rectangle, and the shape. And so you can see the closer the ellipses here are, I cannot point anywhere. The ellipses are the shape, and the bounding rect is the rectangle around them. And it all boils down to the discussion we had with the question coming from somewhere around here just before lunch, namely, how am I going to have my mouse hovering over my items, and so that it will very fastly highlight the items? Well, first of all, it needs to know which item you're hovering over. And that's this binary partition tree again. That is using, of course, the rectangles. And once we have decided that our mouse is over the whale, then it will go and see, is it really over the whale? Up in our example, we could easily be outside one of those, and it will then be telling, no, you're not really over the whale, despite that the bounding rect said that you are. So the bounding rect needs to be really, really super fast, while the shape needs to be really, really super accurate enough. If it's fast too, that's just an added bonus.
Right. And that's, so the common implementation of bounding rect should really be just returning a member function. You shouldn't even do any kind of calculations there, because that's really one of the performance hotspots if you have a lot of these items. And of course, the bounding rect should be minimal if you can do that reasonably fast. So you can make it as big as you want. It will still work if the shape is precise. But of course, you will lose a lot of performance by making it too big. So make it as minimal as possible, not too small, because then you will get painting artifacts. But that's definitely one of the things you want to optimize if you have a large amount of items from a specific type. Right. And then, of course, you want to get this stuff onto the screen. For that, you override the paint method. We mentioned that already. And in there, the item is responsible for drawing itself. The way you do the drawing is the same, from QWidgets. You get a QPainter pointer in there, and on that you have all the drawing primitives that you know from the widget world. The painter is already transformed to the right place on the screen, so you can just draw in there using your item coordinate system. You don't have to worry about where this actually ends up on the screen. If you have an item that has holes in it or consists of elements that are not connected, so if you have transparent background, you don't draw on that, and then graphics view will automatically show the stuff that's behind in these areas.
Of course, if you have a hole in your widget and you click on that, or not your widget, your item, you click on that item, then of course whatever you see through the hole is what is supposed to be activated, not your item. So it's of course important that the shape that you return, which is will not include the whole part. So it should exclude the holes, otherwise the item will take action on that.
Right. So this is about making it visually transparent. Shape is about making it transparent for the event handling, so that the events go to whatever is behind the item. And as we already mentioned, the shape can be completely arbitrary, holes, non-connected items, whatever you want. And you can even change that dynamically by just updating shape and returning different forms there for your item. And of course, you also need to update bounding rect in this case to still contain your item.
So, Volker, will QGraphics View prevent me from painting outside my item? Trick question. No, it will not. What will happen if I paint outside my item? Do you know how much we pay this guy and he doesn't even know? Jesus. If you paint outside your item, it will be painted outside your item. And what's the consequence of that? That QGraphics View do not know that you painted on that. So if we'll show you a small thingy to make you go to sleep soonish, your eyes are getting heavier and heavier. And if I'm painting outside of the item, and I'll show you what will happen, QGraphics View will not make sure that when my item is moving away from that area that it should repaint what is underneath. And you'll just get graphics artifacts, which is one of those things, of course, Volker knew, that you will be a pain from time to time when you work with QGraphics View, because suddenly you have a QGraphics artifact, or QGraphics, everything's Q. Yeah. So you have a graphics artifact, some lines left behind, and we'll even show you an example, and non-obvious to at least those that are new to QTY. And let's just go straight to that example. Here is the example. It is a pendulum that goes like your eyes are getting heavier and heavier. Can you put that music on again? Okay, never mind. It's a QGraphics item subclass. It implements the two virtual methods that it must implement. Had it not implemented those, you would know that the compiler will complain. The one is paint, taking the QPainter. The other is bounding rect, returning a QRectF. Why is it a QRectF?
Well, if you remember, we said that the scene actually works in logical coordinates, domain units, and that's a floating point value. And therefore, we have all the geometric classes that you know from QPainter in the widget world, also in an F version for floating points. So there's rectF, pointF, lineF, and so on, where you can work with floating point units.
Exactly. Here comes at least a to me was at least non-trivial observation. Your bounding rects do not need, I'm here, your bounding rect do not need to be 0,0 up here. And we'll show you an example here with this one. When I want this one to be going, your eyes are getting heavier and heavier. Notice which point is 0,0. That is the point that my finger is holding here. That point is not changing when I transform. Had it been this one, it would have looked pretty odd here. Your eyes are getting heavier and heavier. And in this situation, we'll actually implement a bounding rect that do not have 0,0 here as the usual one, but here. So your bounding rect is not just about width and height. It's also about specifying which point will the what do you call the parent item, I guess, of this item think of being 0,0 and do transformation around that point.
Right. It's a rectangle, so it's not just the size, but also a starting point, and that defines the origin of our item coordinate system.
And that's what we'll see in this code here. We have let's start with the pendulum, the paint event. That's where we're painting this one here. Now let's start off with the bounding rect. If you look at the image down there, you can see that 0,0 is indeed at this point here, which means that I'm returning this point up here being, I guess, this point up here minus 20,0, and then the width and the height. My paint event, I get a painter, I get a Q-style graphics item, which I'm not using now. Just a second, Volker will tell you where you can find that one. I set the pen to be a black pen that has a pen width thickness. I draw a line from 0,0, that would be here, to 0,100 down here. Then I create a Q radian gradient. I will let Volker explain all the details of those parameters. And I paint a ellipse at this particular paint here. Let's start with the gradient. What are all those parameters? Here's just from cute to all of you with love. This is the thing that you fortunately do not see in Qt 4 anymore. How many of you were around in the Qt 3 days? Not many. Those from the Qt 3 days will remember all those fancy constructors taking 200 parameters and like, what exactly does 0, 120, 20, minus 10, 100, never mind. Go and look it up in the reference documentation. Much more important, my bounding rect is returning minus 20 minus pen width divided by 2. Why am that minus pen width?
Right. That's also something you might know from QPainter in the widget world. If you draw a shape with QPainter, half of the outline is, well, half of the pen width outline is on the outside, half of it is on the inside, which is what Jesper is drawing here.
Something like
that. So if I have a 2-pixel wide pen, 1 pixel will be inside the rectangle, and the other one will be on the outside. So I need to consider that when defining my bounding rect, otherwise it would be too small. And if we have our pendulum, if I define that too small, I will cut off the sides. So these parts might be missing or not repainted correctly. That's how it exactly will look like, depends on what Graphics View currently does there with caching of items and clipping of painters or whatever is behind it. But there's no guarantee on what the parts outside of the bounding rects will actually be rendered like.
Okay. Oh, over there.
Yeah.
Too many screens. Yeah. So let's see if it really works.
Awesome.
That's amazing. Can we make that bigger?
Does it actually scale?
Nope. We should have implemented zooming in this example so we could zoom into that one. But notice how it's going around 0,0 at the top of the line just for the fun of it. Let me just try and implement so that I'm going around another coordinate. So now instead,
That's still the house example.
I will go and change the. So let's just go minus 0, minus pin width, just like we had there. Gee, why haven't you checked that? And you'll see the pendulum doing weird things. Actually, I didn't update my painting code, so I'm still painting in the old, what I believed, old coordinate system. I'm just returning a wrong boundary rect here now.
Yeah, you just reduce the boundary rect by half the width. So what you're returning now is just this part. And everything you paint outside gives, well, undefined behavior. Since graphics view is not aware that you are painting there, so it might not update whatever else is there.
And I'll see if I can do this correctly and just go and update my
painting. We also noticed that the rotation was still correctly referring to the center top there.
Yeah, obviously I'm good at this, so here we are. Well, at least you see that it's rotating around the wrong point now.
Right.
Obviously, I'm still have some problems with the bounding rect and drawing outside and stuff, and that's exactly what you'll see in those situations.
Right. And of course, you could make that rotate correctly by applying a transformation that shifts the origin to wherever you want to rotate it off. So you can always fix that by using the right transformation, but of course it's much easier and much more convenient if the center of the coordinate system is where you actually would expect it, so that you don't have to do this transformations in a more complex way.
And that's what Volker is saying here. It's not rocket science to get the other thing working. You can see the code here in the slot rotate item. That's the one that is actually doing the rotation of the item, and we could just have said m_pendulum dot translate 0, what was that, 20, 0, whatever, and then have that, well, too many coordinates, 0, 20, and then we would have that at the top right there.
It's the same as we did with the house example earlier, which we shifted to the right position, rotated, and then shifted back to have it in the original place.
Yep. Whoa. Okay, that was the painting, and we jumped a bit ahead because we told you we'll talk about collision detection a bit later on, but we already did talk about the rectangle method in there, which has less to do with painting and more to do with the collision detection. We'll now talk about event handling in QGraphics View for the QGraphics View items. There's 2 different levels that we have event handling. We have a low level, which you might know exactly from the widget world, where you can get notified about mouse press events and mouse release and so on. And we got a higher level where there is a method called item change, which will be called on us with semantic changes. And we'll see that in the next few slides here. First, the methods for the input events. Those of you that have tried this stuff in the widget world might recognize all these: mouse press event, mouse move event, mouse release event, mouse double click event, key press, key release, wheel event, context menu event, hover enter, and so on and so on. These are exactly the same thing, except that there is one crucial difference. They all take a QGraphics scene mouse event instead of just a QMouse event. Why is that?
The graphics scene mouse event contains also the translated coordinates into scene coordinates and item coordinates, while the classical mouse event only gives you screen coordinates, so where you actually clicked on the screen. If you use those, you'll get the additional convenience that all the transformations are already handled internally, and you can work directly in your domain units instead of screen pixels. Apart from that, it's exactly the same as the classical mouse event.
Here's a simple example of that stuff. We have a key press event on a QGraphics item. It's whoa. That's not a, that is broken. Is that my item? That sounds like it should be a QGraphics item, right? But it's taking a Q key event, and it should take a QGraphics key event. I guess this example is broken. Anyway,
No,
this
no,
example was supposed to be about zooming.
QKey event is perfectly fine there because QKey event has no coordinates attached to it. So we only need to do the translation for mouse events, which have screen coordinates attached to it. All the other events are exactly the same as we know it from widgets.
Just checking if you're awake.
I am.
So we have the key press event here. Pressing down the plus sign will zoom in, and pressing the minus sign will zoom out. We're calling method zoom, which is implemented elsewhere in this stuff here. And we also have the zooming with the wheel event. The only brokenness about this example now that it's not the QKey event that is a brokenness is that this implements zooming on an item. I mean, that's not what you usually want to see. You would zoom on the whole view, so it would be your Q graphics view class that had this implemented. But anyway, if you had a use case where you wanted to zoom on individual items, that would be how you did.
Right. But nearly exactly the same code works on the Q graphics view as well. So if you want to implement real zoom there, the only difference is that you don't get a graphics scene wheel event, but the real Q wheel event because you're working on a widget.
We also had a high-level event system. So instead of getting a mouse press event and a mouse release event, we'll instead get a what's it called? Just
position change.
Item change, which is just a virtual method that's called on us. It takes a few parameters. It takes a enum telling us what kind of change it is, and it's taking a Q variant with the change value in. So that might be position change. So when remember that the Q graphics view framework has built-in support for for moving the items around. Volker showed you that earlier. So if you move an item around, then instead of you overriding and listening to the mouse press event and so on, you just want Q graphics view to take care of all that stuff for you, and then you'll just override this item change event. As I said, item position change. That is when you're about to change it. You can even return a value from the item change method. That returned value will be the new value. So if you do not want it to move, then you will just turn the original position.
Right.
I think we even have an example of that here. Yep.
Why does it have this strange API with a virtual method that gets variants instead of just using signals and slots?
Well, signals and slots requires a significant thing, doesn't it?
Right.
Our good friend QObject. And these fellows here are not subclasses of QObjects for size issues. If you have 100,000 of these items and they are all want a QObject of 40 bytes, then you suddenly have a real memory consumption there.
Right.
But why not just have a bunch of virtual methods then?
Well, the problem is if you want to extend it at some point, you can't do it in a binary compatible way. So you need.
And when you say you mean those friendly people from Nokia. That's
exactly.
likely it. You'll see that a couple of other places. We'll actually see it later today when we talk about ModelView. We'll see that we have a data method that takes different parameters depending on what data it want. And again, this time it's actually extendable by the user, which would be less imagined here, but still for Nokia to be able to add a new one, that would be impossible in this binary incompatible or binary compatible way.
Right.
So
that's
like that.
Okay, so let's have a look at this bit of example code here. I'm not sure if you mentioned that yet, but there's built-in interaction logic available for graphics item, which you can enable on each item. And one of those flags is for making items movable by the user. So if you set that, the user can actually drag a graphics item and move it around. That's what we saw in one of the example applications earlier. However, you might want to control in which area the user is actually allowed to drag around an item. And here we have the example on how to do this. Whenever the user tries to move their item, we get a call to item change with the change type value item position change. That is before the position actually changed. There's also item position has changed, which is after the fact. So there we have, we don't have the opportunity anymore to override it. But in position change, which we get before the actual change, we can still override that. The new position is, we get that in the second argument in the quevariant. And yeah, we can check if that's within the allowed area. If it's not, we can restrict it. So in this example, we restrict it to the area of the entire scene, which we get from the scene rect. And if it's not in there, we restrict the components of the position that are outside, and then we return that. And the new position we return is, well, then the one that is actually applied to the move. So this gives us the ability to override user input here. And that actually works with all the other built-in interactions like selection and editing and so on as well.
The final thing about QGraphics we saw we need to implement paint. We've seen the event handling here now. The final thing, and important in many situations, we already touched it somewhat, that is collision detection. There are a few different ways that you can do collision detection in both the item and on the scene level. So in the item, we have two methods. We have collides with item specifying another item, so you can check if two items are colliding. You can also ask for which items would be, or which item am I colliding with, and that's the colliding item method. So two different ways that you, on an item, can ask what am I colliding with. There is an item selection mode also actually for the collides with item that tells what collision means to you. Are we talking only about boundaries, or are we talking about overlap or entirely overlap? Similarly, we have a method on a QGraphics scene where we can ask for which items are colliding with a given position or a given rectangle and a given
painter path and polygon.
A given path here. So you can on the level of the QGraphics scene ask for which items. And the obvious example where you might use that is if you want to implement something fancy where you want a different mechanism for handling the user clicking on items than what is built into QGraphics already. And there you could go and say which items did collide with this exact point where I clicked.
Right. And if you combine the previous code example with the collide with, you could have something like only allow dragging the item where it doesn't collide with anything else. So you restrict the user movement to areas where there is no other item, for example. Yeah.
Finally, there is an exercise again here that we will not be doing here in class. But Volker, why don't you go through the code and give people an idea what this looks like? It has many interesting QGraphics concept in there.
Oops. Maybe let me run the solution first so we see what we actually want to implement. So this is a simple graph, 3 nodes, 3 edges in between, and whenever I move the nodes, the connected edges follow. And you also notice that the selected node is highlighted. So this uses 2 of the built-in interaction mechanisms for moving items. So I can drag this around without needing to implement all of this myself. And it also uses the built-in item selection concept, which I also just need to enable on items where I want to support selection. That's not something I need to implement myself. But yeah, let's have a look at the code. Starting from main. Okay, so there's not much interesting in there. let's just go to main view. Why is that different to what I have on the screen? That doesn't match at all.
Mm-hmm.
Ah, no, it's update. Okay. So this is a subclass of graphics view, but I don't think we actually do much on the view itself. No. So the interesting bit is creating our scene in there. We have seen that a few times by now. We create our graphics scene object and then add the items to it that we want to display. And in this case, we have two of our own custom item classes, node item describing the graph nodes, and edge line item describing the graph edges. We'll look at their specific implementation in a bit. For the node items, we just set initial positions. That's boring. For the line items, we set the nodes to which the line is connected to, so that we actually have a complete model of the graph and can automatically update the lines when we move the nodes. And finally, we add that to the scene. So let's have a look at the line item. That's inherited from graphics line item. That's one of the built-in item types that we already have. It's provided by graphics view. We just add a few member variables to store the nodes we are connected to, and we customize the visual appearance a bit by setting a pen. And yeah, we have methods to set the two nodes we are connected to. Those are the ones that we called from main view. And there's one method at the bottom, adjust. That's the one that will actually update the line whenever one of the nodes has changed. So that's something we will be calling from node item. And all it does, it sets the line. This line item is actually showing to a line between the position of the start node and the position of the end node. So we are just using the pointers to the nodes in here. So I think all the interesting bits are in the node item class. Yep, there we go. This is now inheriting graphics item. So this is really a custom item, not based on one of the existing ones, but one where we also do the painting ourselves. In the constructor, we enable the built-in interaction flags that graphics view already provides for us. Namely, is movable, which means the user can actually drag around this item, and selectable for the selection handling. And yeah, to actually get updates about the position changes, we also need to set the item sense geometry changes flag. The reason for that is if a lot of stuff is moving around, you get a lot of calls to item change, and that can be optimized away if you don't really care about it. That's an optimization that was added in Qt 4.6, so you now need to enable that explicitly to actually receive those calls. As in most cases, you don't care for them. It's actually a good thing that this is switched off by default. Right, appending the lines, that's just managing the line items that are connected to us. And then here we have item change, the one we are actually looking for. Here we're now looking for the item position has changed change type. So that's the one we get after the fact, after the move has actually been completed. And that's where we update all the lines that are connected to us. So here we just iterate over all the lines connected to us and call adjust, which we saw earlier will just reset the line it's actually showing. And that's all we need to do to have the line following implemented. And then there's one last thing we have to look at, and that's painting. Oh yeah, bounding rect, shape, everything hard-coded. There's one interesting bit in paint, though, and that's, you remember that when we had the node selected, it showed in a slightly different way, like brighter gradient. And that's where the QStyleOption graphics item argument in paint comes in, because that allows you to query the state of all these built-in interaction options. So with that, you can, like you see here, query if it's currently selected. And if it is, we change the gradient slightly to reflect that in the UI. And the same you can do with focus and whatever else is available there. So that's where you actually need this option. For items that don't have any interaction, you usually can ignore this argument. Yeah, I think that's about it.
That's about it. So we've seen QGraphics item, 2 classes we definitely need to subclass. There is the paint, there is the bounding rect. We do not need to implement the shape. What happens if we don't?
It defaults to bounding rect. So
exactly.
As long as you have something rectangle shaped, that's fine, but then you could just use rect item.
And we've seen that all these things, the paint, of course, is for painting, the bounding rect and the shape is for that partitioning tree that we've seen up here several times by now, for making that fast. So if, again, there was a question earlier on, if somebody had something that was pretty slow, make sure that you have a really, really fast bounding rect and that your shape are accurate, and then mess with the depth of that tree. That concludes our section on QGraphics view. Next topic is multithreading. But before we continue into that, to see if there's just a few questions on QGraphics view again. Yeah, guy with microphone. Wake up!
Is there an easy way to paint all of a graphics item and its children to an image, for example?
The graphics scene has methods for rendering into basically any paint device, SVG or whatever you want. I'm not sure if that's available for items.
So what are you trying to do? Make a screenshot of your stuff, or?
I needed to have an image representation of it because I needed to move the stuff to a different parent. So I wanted to show the image presentation of it, and that turned out to be very complicated to do.
So you have a solution already, just testing us?
I'm
okay.
using a QGraphics effect to grab the image, but I hoped there's something more easier, because that also is not very easy to do.
Okay.
I'm not aware of anything that allows you to actually render the apps. You might be able to call paint manually on the subtree, but then you have to deal with all the transformations yourself, and then you're basically re-implementing graphics scene, which you probably want to avoid. You could hide everything else and then use render on the graphics scene. But I don't think it's really made for just rendering a subtree of items. Could be
Anybody
useful,
could help us here? Anybody know any easy way? There was a question just before the break. Now I just remember somebody asking about, can you run a video stream in there? And somebody was kind enough in the break to come up and say, yes, I had actually already did that. Can I see the hand of that guy that said that? Who came to? Two people saying, I only had one person up here. That guy down there. Can you stand up? And can you look at that guy over there? Go and talk to him afterwards. He already did have fun and playback inside QGraphics item. So the question was, can we do that? Yes, there's your proof. And again, it depends on the speed of your CPU and graphics chips and everything, how nice and smooth it's going to be. OK, let's carry on with some multithreading.